Jim McGregor here for another TIRIAScast. Thank you for joining us. I'm here with Pradeep, and we're going to be talking about the CPU architecture on the Snapdragon X2 Elite product series. We're here at Qualcomm for their architecture day on the new product line. So, Pradeep, you want to introduce yourself really quick?
Yes, so my name is Pradeep Kanapathipillai, and I am the Vice President of Engineering at Qualcomm, and I lead CPU architecture and design.
Okay. Well, Pradeep, obviously, you guys have taken a whole nother step forward with this generation. The Oryon CPU, this is your second generation. You know, key challenges: make it wider, make it deeper, make it faster, even going up to 5 gigahertz with this generation for a boost frequency. Can you tell us some of the major enhancements that you did with this generation? Because I know there were a lot of them.
Yeah, so there are over 100 features and new architectures and enhancements that we put into the design between Gen 1 Oryon CPU and Gen 3. And if I were to classify those into a few categories, those would be IPC enhancement features that uplift the IPC of the machine for performance. What I call PPA features, which is power and performance and area uplifting or improvement features, which includes energy efficiency improvements. Architecture level features at the ISA level, power management features, memory subsystem improvements in terms of cache hierarchy, latency of access, that sort of thing, as well as I would classify as other, which is everything else, debug, trace, and all sorts of things that we need to have in silicon that also have a gen-over-gen improvements, not just performance and energy.
So basically everything. This is almost a brand new architecture. Well, it's still based on the Oryon, but significant enhancement over the previous generation.
Correct.
And you did 2 different cores this time. You did a prime core and a performance core. What are the major differences between the two?
So the differences and the reason for having the 2 types of cores is just like what we have in the industry, where to get the full dynamic range from peak performance down to the lowest power consumption levels, the same core type would not do. It just will not work. And also, most workloads and applications do not need a high IPC machine like the prime core, which is the hardware IPC is 9. Most workloads will need much less. So for those reasons, it makes sense to have a different core type that is focused more towards energy efficiency. In our case, we are calling it the performance cores, and those target a balance of performance and energy efficiency. So in this design, we've got 18 CPUs, 12 of them prime cores, and 6 of them performance cores.
Now, and this is unique because, when I look at this architecture, it's significantly different than what we've seen with other PC architectures. Typically you start with the CPU core and build out, but if you look at this SoC, it's not laid out like a typical PC processor, with the cores and the memory being the central focus. You actually architected this more like a custom SoC, where you put the cores in different locations around the chip, even the GPU at a, extreme location on the chip. Can you talk about, how obviously that design of that impacted not only the CPU cores, but also the SoC design? I mean, how different is this from, trying to architect something that was just a basic processor?
For an application processor SoC for the client compute, certainly a number of different pieces have to be there: CPU, GPU, NPU, camera, subsystem, sensors, and so forth. And each of them take a certain amount of silicon real estate. In terms of the flow planning piece that he brought up, right, the placement of the CPUs versus GPUs on the SoC die, that is a trade-off that our physical design experts who do the SoC flow planning make decisions on, based on which subsystem stands to benefit from being closest in terms of coherence fabric, CPU to DRAM path, effectively, right? So CPU through its L1 and L2 caches, through the coherence fabric, through the memory controller which hosts this system level cache, that path, the CPU as an agent would like it to be optimized the shortest latency. So that drives the decisions in some of these flow planning pieces.
One thing I was really impressed with the CPU architecture is the fact that you have 3 clusters of 6 cores each, and you have the ability to boost each cluster separately. So you can boost, 1, 2, 3, or 3 cores on, the prime on 2 of the prime clusters or on the performance cluster. I mean, that's a significant change from anything I've seen before. Is there any other challenges associated with that? I mean, how do you, obviously a lot of that's handled through firmware and everything else, but are there also some hardware controls to be able to boost all those different cores separately?
Well, there are lots of hardware pieces that play into that story. So in our design, each of the clusters is an independent DVFS domain, dynamic voltage frequency scaling domain. So each cluster has its own set of voltage rails that is independently voltage frequency controlled by hardware in that cluster, certainly with input from firmware and input from high-level OS, but most of the transitions are hardware managed. And so coming back to your question on the boost frequencies, when 1 core is active per cluster, as we talked about this morning, that effectively takes advantage of this concept of dynamic guard banding. So that's a load line effect. When more cores turn on, the current draw increases, the current draw placed on the voltage rail increases. And so there's a certain load line curve when you plot voltage across current. And all of the margins that you can harvest in terms of getting the highest frequency for a given voltage or the lowest voltage for a given frequency, that plays into this. And so to be able to get the highest frequency when just 1 core is active, that's the 5 gigahertz that we talked about this morning. And then when more cores turn on in that same cluster, then we step down into the next staircase step in terms of frequency. And that plays out on a per cluster basis. So up to 2 cores active in that entire CPU subsystem at 5 gigahertz.
And the way they described it, you have basically power rails for just about every function on the chip. So each cluster is going to have its own power rail and everything associated with that. So, and it's interesting because we've seen kind of the pluses and minuses of other architectural considerations, such as multi-threading go in and out of PC processors in the past. You haven't used multi-threading. Is that something that you see as a positive maybe for the future, or something that just doesn't fit the segments that you're targeting?
Simultaneous multi-threading,
yes.
SMT. SMT, so here's my take on it. I mean, we within Qualcomm, we look at all the technologies for future products, although I cannot comment on the details on what's coming in the pipeline. But as a concept, SMT has its place. But if you're implementing a truly fine-grained simultaneous multi-threading, not the coarse-grained switch-on multi-threading, but truly fine-grained instruction-level multi-threading, where the instructions from thread 0 and thread 1, let's say for a two-way SMT, flows inline through all the microarchitectural structures, and let's say that hardware minimizes any cross-thread starvation cases, etc. That is fairly costly in area and power.
Yes.
And so one has to comprehend that downside with respect to any upside that the SMT might bring in terms of performance, single-thread performance or multi-thread performance. And at this juncture, SMT did not make sense, which is why we did not add that into our silicon. But that's not to say that we will stop looking at it.
Well, I am amazed. The performance you saw from the first generation, the fact that you were able to enhance it significantly for this generation. You know, as we go forward, I would expect that we're going to continue to see those enhancements with core changes, with different core configurations, layouts, everything else. You guys have done a great job there. So anything else we should, you know, take away from, you know, the architecture, especially the CPU architecture? I mean, this is a very unique SoC for PCs. So what else should we take away?
This is our third generation custom CPU at Qualcomm. I cannot comment on forward-looking products, but I'll just say that we have a very rich and vibrant roadmap ahead on the CPU. And there are plenty of things that we look at and we decide what goes into what future product. So there is more to come.
Thank you very much, Pradeep. Thank you for joining me today.
Absolutely.
And if you like this TIRIAScast, please like and subscribe. And if you have any recommendations for future ones, please reach out and let myself know at jim@TIRIASresearch.com or francis@TIRIASresearch.com. Thank you.